Um, okay. 자, I'd like to remind you that the chapters we are planning to learn in this class, solid mechanics has two divisions, mechanics 1 and 2, and we are in mechanics, solid mechanics 2. So we are studying chapter 5, and then followed by the 7, 11, and so on. And we are still in the chapter 5, and next one will be the chapter 7. And the chapter 5, I cannot emphasize how important it is, especially this stress transformation. While you may forget all the equations about the stress transformation equation and so on, but the most important point is what is the stress transformations? Understanding its meaning is the critical in understanding the following all the solid mechanics. The main reason is that I just like to remind you of what we already covered. This is the 351 flow chart, and on the body, a force will apply to the material or body, and then it will deform. This is the 3 point is about the external load and externally given the materials and then externally observe the deformations. Now inside the some they have to be in equilibrium. Their stresses will develop. Of course, the strain also developed. So stress and strains are kind of a behavior or the physical quantity we have to understand. So simply stress you can say is related to a force, and strain is related to a deformation. But not such a word is not enough to describe fully the stress and strain. It is because the force and strain is no longer one-dimensional. Inside the body is a three-dimensional, so we need to understand the meaning of the stress in three-dimensional space, and also the strain as well. The stress now, when we design the structures under this kind of a load, the stress will develop inside, and then the stress have to be less than strength. And the material properties inside also we have Young's modulus and Poisson's ratio and so on. So stress and strains are related through stiffness, and this strain field have to meet deformation condition, and stress distribution have to meet equilibrium condition inside the body. So again, this 351 flow chart needs to be recalled as often as possible, and then I'm sure that this will guide you or guide us to all the subject we are learning in this class. So again, we are in this stress in this category, and the stress will be less than the strength, and for the structure to be safe without any failure. So we are learning the stress. Okay. Again, please keep this flow chart in mind. And then we are at the chapter 5. So chapter 5, this is a summary of the stress transformations. Again, we have a body. Well, in this case, we are considering only two-dimensional space, two-dimensional stresses, but nothing is a two-dimension, actually. So actually, it's a part of a three-dimension. Anyhow, there is a point O, and then the stress is given at that point. We have a 2x2 stresses. We already know the definitions. Definition is that sigma xx and sigma yx, this is the two component which occurs on the x plane. And then if we cut this way, there will be another two stress components. This is two stress components which occur in the y plane. So this, I would say, y plane, and this is x plane and y plane. So you can imagine this is the planes. And now this one, I would say, this one is the x directional force, and this is the y directional force. I'll say this is forces. Cannot say force because the distribution is not exactly the force, but for the purpose of easy understanding, I'll just call them forces. So anyhow, as you can see, this is the x directional force, and this is the x directional force. But depending on the plane where it occurs, this sigma xx will be the normal force, and this sigma xy will be the shear force. And of course, this is the y direction, and this is the y direction. So again, please make sure you understand that direction of a force, but the direction of area is the critical. So anyhow, usually this is the given quantities. So we're starting with this four stress components given at a point O, and now we are trying to find the what kind of a stress will occur at a certain plane. Certain plane is means that, let's say we cut through this here, and then what will happen to that surface here? So there will be again the two stress component. One is the normal to the surface. The other one is the tangent to the surface. That is the two plane. So we can say that this is the exactly same as the previous definitions. This is a plane. We will have a two component, and also we can have another plane, which is the vertical to x plane is called so x prime plane and y prime plane, and then we have two components, and then as you can see, this is the x component force and y component force. So we kind of understand at a point O, we have a four component, but with the two different plane, we have another component. And there should be some relations, these four components, in terms of this originally given four stresses with a theta angle. This is the theta. Okay, so as you can see that, well, we already observed that sigma x prime y prime is always the y prime x prime. This guy and then this guy is always the same. If I draw, well, here same thing. This guy and this guy is always the same. We already checked, learn why they are same. Well, this guy we can draw here, and because of a force equilibrium, we'll have a reaction like that, and this guy will appear here, and then our reaction will be like that. And now, as you can see, all the force equilibrium, this guy will be the same, and that guy is the same. But the one thing we have to have another equation, another equilibrium is the rotation. So this guy, this two pair, one pair will rotate this one, and this one will rotate this way. So that's why simply we can say that this sigma xy and the sigma yx have to be the same. Is a really important, very simple but very powerful. So anyhow, that's why it's enough to consider three components, and it's enough to in terms of three components, and all others are function of or theta here. So sometimes you may forget all the equation. Well, you don't have to remember that, but sometimes you may want to remember. Actually, there is an easy way to remember that. I will tell you the secret. See, this is x prime and x prime equal. Now here, sigma xx, you list all the components. But say x prime and x prime x, okay, x prime is what? This guy, and x is what? Actually, you can draw here. What is the angle between that? Well, between that is a theta, right? So whatever the two axes, there will be an angle between those two axes, and then a cosine them. So x prime x, there will be a cosine theta. And there is another one, x prime and x, and x prime and x, there is another cosine. Okay, so cosine scale. That's why we have a cosine scale. And plus sigma yy. Well, what component do we have? We have a sigma xx, yy, and xy plus sigma yx. So we do the same procedure, say x prime and y. Now it's x prime and y. X prime and y is this one. So this one will be now is 90 degree minus the theta. And cosine of this, what is that? Will be the sine theta, right? So again, the whatever angle between two axes, you just have this cosine of them, and then in this case it give us the 90 minus the theta. Cosine means that sine, and same x prime and y, while another sine, so scale. And next one is the x and y, and x prime and x, what is the angle? Theta, so cosine theta. And x prime and y, what is that? Well, that's the sine theta. And here, x prime and y will be the sine theta, and then x prime and x will be a cosine theta. So as we already know, this is the these two stress components are same. Those are shear stresses. So that's why we don't need to repeat. We just say twice. See, that's the one we this exactly same equation. this was obtained from considering the equilibrium, but we can simply say like this. And the same for here, exactly follow what we have done here, and same here. So x prime and x, there will be a 90 degree minus theta, cosine and sine, and so on. This is rules. Actually, these rules we can also observe in the force equilibrium. Say here, you know, we are much familiar with this force transformation. We have a force, and now x prime and x. What is x prime? This is the x prime, right? This is the x prime, and the original x is this one. So x prime and x is a cosine theta. See, we have only one index, so only one cosine theta. And x prime and y, x prime and y, and there is the same x prime and y. This is the 90 degree minus theta. Cosine of this will give us the sine theta, right? And now y prime and y, sorry, this is x. Y prime and x, what is that? Y prime is this guy, right? The y prime and x here. So actually, in this case, 90 plus theta, because this is a theta, and cosine, what is that? Well, I hope you guys didn't forget. This is simply minus sine theta, and so on. So actually, these rules, this procedure will equally apply to a transformation of a force, and just keep that in mind. In case you forget the equations, you can follow these simple procedures. Then you can get these terms as well. Okay. Okay, so again, this is not a new subject. This is just a reminding or a review of our previous class. Now, we like to do some mathematical manipulation, such as the cosine square theta will be replaced with 1 plus cosine 2 theta, and sine square is replaced by this. And then here you had we had 2 cosine theta and sine theta, and it can be replaced like this. Now here is the, rather than square, and then this is a twice multiplication, so same order as a square. Now instead of a theta, we replace 2 times of a theta, right? 2 times of a theta, and then this guy and this guy, we got this term, and the other term we got this term, and cosine theta, and this like that. So we do the same for the y prime, and so on. And this is the first step toward the Mohr circle. To draw the Mohr circle or understand Mohr circle, this is a first step in terms of mathematical equations. So as you can see that once we have this term, it's not easy to relate to a circle, but the just the let's say skip all the procedure. But here is the how we draw the Mohr circle. Mohr circle, please don't forget that x-axis represent normal stresses, and this is a shear stress. And so choose a set of XY coordinate axis, identify and this, and then draw a sort of a coordinate system, and then plot the point, and then label then X and vertical. So up to here, what it says is that, let's say we start with a sigma XX and sigma XY or YX, it doesn't matter, sigma YX and sigma YY. So we have once we have this plane, we like to draw the Mohr circle. So first step is the important point is the plot the X, large X. What is that? Well, let's say this is the two components representing one point. So sigma XX and sigma XY. So we just get the point here, and here another one, YY and X. So this is the X, but it's not difficult. And plot the point, the labeled at Y, and this one now here, okay? So this one will be a YY and XY. We have a point here. And then simply draw a line, line connecting to these 2 points. And then I'm sure that there will be a cross point here. This is a center of a radius. And all you need to do is just draw the circle with this radius. So any rotation now with 2 theta, okay, not just a theta, 2 theta, and this will be X prime, and this will be the Y prime. So actually, that's it. Very straightforward. But one thing, the one you to remember is that here, X, the if now the point is the sigma XY, is it positive or negative? Depending on this situation, this will be location of X in this Y-axis will be different from Y. But simply because we like to have this and X and Y, we have like to have a diameter. So meaning that if this is the lower of this vertical axis, then this will be the upper. So the in drawing, if this is a sigma XY is the positive, well, this drawing is slightly different from what we used to have. Let me. Okay. So if this is the positive, this will be the lower hand in a negative side, and then this one will be the positive. This will be go to upper zone. That's the all you need to remember, which is slightly different from a conventional coordinate system. And again, once you rotate, you got a new point. Now this is the upper. Then what does it mean? This will be a negative, because again the sigma XY is the positive. Then X will be a lower negative zone. The lower in X sigma XY. And the positive and sigma XY for the Y point will be upper zone. Okay, so the looks like many steps, but not that many. Simply you pick the 2 points, okay? You pick the 2 point with a careful attention to a sigma, the sign of a sigma xy, and draw the diameter, and then make the circle. That's it. That's the what we learn from Excel as well. So let's try to draw a case. This is a simple sigma 0 and nothing else. I recommend you to always draw this. So sigma 0, and there is a 0. And then y also 0. So sigma 0 and 0 is a coordinate will be here. This is a sigma 0. And the shear will be a 0. So that is the x. And 0 will be this point. So it's clear that we have a x and y. Now, once you have a x and y, you can rotate 2 theta, and you will have a x prime, and this guy will have a y prime. And then the coordinate, see, this guy, this much will be the sigma x prime, y prime, and this one will be sigma, sigma x prime, this is a x prime, y prime. Okay, so if you have a circle, all you need to do is just have a coordinate in this plane circle. All you need to do just read the value. Well, you don't have to use this Mohr circle, but it gives us real insight into the transformation of the stresses. What is that? As you can see that no matter how much we rotate, the maximum possible tension load is here. Minimum possible tension, normal stress is here. Maximum possible shear stress will be here and here, right? Okay, what does it mean? Meaning that once this is subject to this object like that, and then there will be a stress occur like that. Now we like to know how much the normal stresses and shear stress occur and at a inclined surface like that. So this normal stress will be represented by this axis, and then this shear stress is represented by here. So as you can see, no matter how much you rotate, this is the maximum possible normal stress. This is the maximum possible shear stress. So here simply this is a 2 theta, and 2 theta is a 90 degree. This is a 90 degree. So theta will be the 45 degree. So as you can see that certain shear stresses will occur, and this shear stress will be the maximum at an angle of the 45 degree. Oh, this is a so important observations. Again, when we have a tension, this is important. Tension, the maximum stress, shear stress will occur at a 45 surface. And how big is this one? And that is this much. And this sigma 0 was this much. As you can see that this one is simply what? Half of the sigma 0. Because this is a radius, this is a diameter. So you can immediately understand what will be the maximum shear stress in this plane. And then see, let's get the another one. Here. Over here, this point, we call them C, center of a radius, a center of a circle. And then simply from this equation, we can get the sigma 0 divided by 2. And radius R is the you already have an equation. Well, you may forget this equation, but always you can see that this is the this guy, and I'm sorry, this is this guy, and that is the vertical line. We have a radius, so you can simply get this one. So here is the represent the maximum shear, and now on a different case. I highly recommend you represent them in a 2x2 tensor, the sigma 0, no shear. And why? Well, minus sigma 0 because it's a compression, and 0. And then you forget, you mark this one, x, so this will be sigma 0 and 0. And here, minus, what does it mean? Minus means that x is from left-hand side, minus sigma 0 and 0. So this is the x and y. And now you make the circle. You can see maximum stress, and then any stress you can draw. You can see that. Now this one is only sigma 0 as a shear, no normal stress. So 0 and sigma 0, and the sigma 0 and 0. So let's have a x. X is this one. So sigma x is 0. So this axis, see this is a sigma xx, sigma y. Now sigma 0 is a shear. This is a shear term, and here we already got a rule saying that if this is a positive, this shear stress is positive, let's locate it in the lower side. And this is the same. This is the 0, and sigma 6 is a positive, and this will be the y. So draw line, and then a circle, and this is the one. See here, another, similar observation is that, let's say we, here and there, this is a two very important point. And the what is the maximum compression and maximum tension, which occur again to theta. So theta will be the 45. What does it mean? If we have a draw like this in the 45 direction, the axis, okay, axis will be a tension. So tension, right? So this much tension. And then this one is a negative. Negative means this way. So shear stress will be equivalent to the tension compression state, 45 degree. Okay, this is a very important. Please remember this one. Just a pure shear will be equivalent into a tension and compression. Well, actually, you don't have to remember anything. You can just say, you have this guy and that guy. It looks like something goes this way, right? And then this guy and that guy. Well, we have something like that. But that is not enough. We need to have a component like this and like that. So if we have a 45, this is the 45 and tension and compression in a surface. This is the important point. Okay, well, we review all the class we observe, and this is the we already observe. I like to. Okay, this is all kinds of mathematical equations, but more important point is that how to relate this mathematical expression with the real situation. This is one example. Say we already observed this one. We have a tension. Okay, we have a tension, and then this is say metal. metal, the steel, for example, and the metal is the weak under shear. This is a well-known behavior. Metal is very weak under shear stress. Now here, this is a tension. So this guy is a tension, and only tension. There is no shear. What does it mean? So this material will not fail. What will be the maximum shear stress? As we already know, 45. 45, we have this shear stress is a maximum. So this metal is a weak under shear, and where is the maximum shear stress? In the 45 degree. That's why this guy starts have a we call it necking in 45. So it's gradually like this, and then finally failure. That is what we have observed. That is how we relate this stress transformation and then a real behavior, as you can see here. And under tension in the 45, the shear is the maximum, and the metal will fail in 45. Why? Because metal is the weakest weak under shear stress. This is the bottom line. And we can observe many things. But as long as you understand this Mohs circle, other how to calculate the angle, how to calculate the maximum shear stress is just the mathematics and trivia. But more important point is the you understanding. You may forget this one, but who cares? You always look at the class notes, and then you can ask for the ask ChatGPT what are the maximum stresses and so on. And then this one, by the way, these 2 points, as we already know, these are very important points. This is called principal stresses. Principal stresses, we call P1 and P2, or max or mean. So if we given the sigma x and xx and sigma xy and sigma xy and sigma yy, from this given, we simply calculate this one. This will be this point. So in general, here we have like this, and then so this point will be drawn here, the x, and here will be the y, and then calculate this. How to calculate that? We can simply, from this geometry, you can see that this is a radius. This is a radius. As you can see, this one and that, you have identity like this, and you got the R, and what is this? This is the C. So C, and C, this is called C plus R, and this is simply C minus R. That's why we have a plus minus. Well, again, we don't need to pay much attention to equation, but try to understand the concept, and then we can always really help us to design our materials and so on. So this is the same thing. Okay. Here the strain, but let's jump to chapter 7. Okay, as a schedules. Chapter 7 is the failure criterion and then stress concentration, so on and so on. But most important point is the the failure criterion as a continuation of chapter 5. chapter 5, we understood the definition of a stress, and we also understood the concept of a stress transformation, which give us the normal stress and shear stress at a certain point, a certain plane, right? Well, I keep drawing the same one, but let's say we have a stress like this, and then we like to know how much stress we have on a certain plane, how much the normal and how much the shear. And this is a two plane, and then also we have another vertical, we have a normal and shear. Anyhow, the question is that, will this material fail or not? That's the answer. That's the question we like to answer. So this is the failure criteria. The concept is very simple, okay? Failure criterion, why do we need to learn? We like to answer to the question whether the material will fail under certain stress state or not. So let's pay attention to a uniaxial stress case. We already know this is a material under stresses, very simple uniaxial stress. We have a sigma xx, and this is a strain. So stress strain, this will deform like that. This is extension, right? And this much will be determined by the Young's modulus, stiffness, which you already know. And this is a contraction which occur under tension. And this is related to Poisson's ratio and Young's modulus. But now the main point is that we observe, forget about this Young's modulus and Poisson's ratio. What we like to know is that we like to draw the stress strain curve, and initially stress and strain will make the pretty much very linear line, and then there's now something goes on. This is a point as we just to review. There is a shear stress maximum occur, and then a material will start to fail, and then there is some nonlinearity is occur, and then finally it breaks. The so this is very typical. And then when we design the structure like this under sigma x, we observe this stress. The limit stress is the yield stress. Okay, yield strength. This is the important point. Yield strength. So when we design, we like to say that sigma xx, which can be easily calculated by the P divided by the cross section A, should be less than this yield strength. What if sigma xx is larger than sigma y, which means that this point? Well, material will goes over this one. But what will happen? Actually, what will happen after this yield is that is an unloading situation. Unloading means that this guy unload would not follow this path. This will be a very will be desired, but it's not like that. Unload will go like this. This is almost same slope as the Young's modulus, and then we over here. We are reaching here. What is this point? This point, we don't have any stress, right? Stress is zero, but we have a permanent strain. This is a certain permanent strain, I will call P. What does it mean? Meaning that we have a stress, okay, we apply, and then this is a sigma xx larger than sigma y, then this guy will be, even though sigma xx is 0, we didn't apply. This is the unknown, and then this is the longer than original length, right? This is the epsilon p, this is the residue. So this is not desirable. This means that we call this is a plastic strain, a permanent plastic strain, permanent strain. So this is the permanent strain occur and then remain, which will totally destroy the internal situation of the body. While plastic is not a desirable status, which designer didn't mean to consider. So this kind of a permanent strain should not occur in structures. For example, airplane or the vehicles you design, but whenever you don't drive the car should go back to original status. After long drive, while the drive has a permanent deform, and which is different from original, while you don't want that, nobody want that. The vehicle will have a totally different situation, easy to failure, easy to breakdown. So anyhow, in design, okay, this is important, but it's very simple and very important. When we design, the stress, whatever stress, should be less than this. So any point here, we go back here, and then we ride the vehicle again, and then unload, this has to go back. So always go back and forth like this, okay? Never try to reach this one. Well, you can design as close as this is okay, but have to be returned back. So this is the concept of the stress should be less than strength, okay? Stress should be less than strength. Easy. Sigma, you calculate the sigma, you apply the P in a bar with a cross section A, and then this is a stress, this is a stress, and this make sure that this stress is less than yield strength. Of course, in real design, we have to have a little bit of a safety factor, because when we design, we may have a certain case that, the load we consider may exceed the design load. The material might have some defect inside, so we always have some sort of a safety factor. That is the important in real design. But as long as we understand this concept, we can introduce a safety factor anytime. Well, to make a long story short, very simple. The stresses should be less than strength. Strength here is the yield strength, and stress will be simply calculate that if this is a one-dimension case, 1D, like this. Okay. But now question arise easily, say, what will happen? We have not only sigma xx, but we also have a sigma yy, and we also have a sigma xy. Now we have a three components, sigma xx and sigma yy. We have a 1, 2, 3. Well, this is the same. Three component. If this is a one component, we do know sigma xx should be less than yield strength. Now, what kind of equation, what kind of rules do we have to meet when we have a three component? That's the question we like to answer. Well, long times ago, people were trying to come up with a certain rules and certain equation, and by observing the material behavior. And then finally, we got a very famous and very important theory. Okay, this is a theory, Van Mises yield criteria. it starts from like this. Okay, experimentally, okay, this is not a physical derivation. This is a theory. Theory means that sort of based on the observation, based on the facts, but this is not a physical behavior. But anyhow, experimentally observed that a function in the function in terms of a principal stress reach a constant value when a failure occurs. Okay, we already learned about the sigma 1 and sigma 2, which is the principal stress. Principal stress always the stress that sigma shear stress would not occur. That is the principal stress. You remember the principal stress always this one, that, and means that no shear stress. So when we have a given like this, and we are trying to find the what kind of normal stress and shear stress, and we can always find the angle or certain direction where no shear stress occur. So so this is a sigma and sigma 2, and this is a principal stress. And experimentally observed, this is important, and they observe that they always, when material fail, whatever function reach the constant value. This is very important observations. It gives us a real clue to reach failure criteria. Okay, the principal stress, a certain function, we don't know yet, certain function of this principal stress will reach certain value, always the same value when material fail. Constant. It doesn't matter how complicated, it doesn't matter how simple, it always reaches the certain value. And this formula, now they observe and propose this way. Sigma 1 minus 2 square, sigma 2 minus 3, and sigma 3 minus 1. Now we are actually studying, I'm trying to draw the three-dimensional status like this. Okay. So we do not only this guy, but we may have find another one, which will be called sigma 3. How to calculate this one? Well, you don't have to know, but conceptually you already know how to calculate the sigma 1 and sigma 2. That's enough. But you can easily imagine that there could be another principal strain in third direction. Yes, you are right. We have a 3 component. Now sigma 1 square 2 minus 3 and 3 minus 1. I just want to tell you that what this means. Minus sigma 2 minus sigma 2. I mean sigma 1 minus sigma 2. This is the sigma 1 minus sigma 2, and the minus means that, what does it mean? This is a radius or diameter. So which is the same as this shear stress. This one is a similar concept to a maximum shear stress. You know, another plane means that this is the plane we consider like this, but we can consider this plane. We may have another plane. It's difficult to draw, but this plane, and the another one will be this plane. So if we have a stress at a point, we can have not just the XY plane, but we can consider XZ plane and ZYZ plane. So depending on the plane, we may have 2 principal stresses, so totally 3, and then each plane we have a maximum shear stress, and the scale will be always a constant. Okay, constant. Then what is the constant? Well, this constant is obtained by applying this equation to a one-dimensional case. One-dimensional, what does it mean? Sigma 1, when it reaches the yield strength, remember the this stress, this one, this is a sigma x and sigma epsilon y. So this is a one-dimensional case. So sigma 1 is reach the sigma yield strength. This is the yield strength, and this one is the yield strength. So the others are all zero because we don't have other stresses. And then we come up with 2 times of sigma square. This constant was unknown, but now we can see that this is twice of a sigma y square because they observed that this is a constant. So constant can be simply obtained from a one-dimensional stress test experiment, and this is the 2-scale one. And then this guy, we put it here, or this guy, we put it here, and then a little bit of manipulations, and this sigma, see this here, and then divide by 2, and this, and then we have to have this stress, okay, principal stress, and divide by, and the root have to be less than sigma y, okay? Please remember that this should be less than sigma y. This can be very special. Let's call equivalent stress. What this call, let's call this one is the von Mises stress. So von Mises stress is given in terms of principal stress is like this. Well, you may forget this equation, but it's hard to forget. Just the difference of each principal stress and scale and root. Okay. So this is the one we got it. And 2-dimensional case is sigma 3 equals 0, and then sigma 3 equals 0, and put 0, 0, 0, and then this equation get simply like that. Okay, simply got this one. So if we plot in a plane, this is a sigma 1 and sigma 2 plane, okay? It's not the Mohr circle, don't get confused. We simply have a, say a sigma 1 and the sigma 2. You may have a very large sigma 1 and small sigma 1, small sigma 2. And this is the this point, right? Large sigma 1 and small, and this is a tension. Or this is a very small, tension, and then this is a tension. Where is it? Well, here is the, here will be the point, something. But now we can see that from this equation, we have a criterion, graph, saying that within this, material will be safe. Material will not fail. But above the outside of this graph, here or here, what will happen? Material will fail. Material will have a plastic. Material will have a permanent deformation after unloading. So we don't want to design like that. Okay, so be sure to have a principal stress within this criteria. Okay, that's the 2-dimensional case. Now Transca yield Korean yield and then criterion in 3-dimensional state. Well, the von Mises is one, and then another theory. Okay, this is another theory. You may come up with your own theory, no problems. But the point is the people will accept one. So the Transca now is a different, little bit different equation. Sigma 1 minus 2 and divide by 2, and this one maximum will be a called sigma tau maximum, and this is always the certain, I would say, constant. This constant value can be obtained by the, again, simple tension equation. So tension equation, you can see that sigma 1, what was that? Sigma yield, and this one is a sigma yield. Others will be 0. So from this, we can have, this is the same, maximum will be like this, and this is the constant. So we can say this is the yield strength divided by 2. This is actually very is clear because the tension here, the maximum shear will be the half of this yield, if this is a yield. So you can say that half will disappear, and simply maximum of sigma 1 minus 2, 2 minus 3, and 3 minus 1 should be less than sigma yield. Okay, so that's the one. I'll write it here. Maximum sigma 1 minus 2 and 2 minus 3 and 3 minus 1 should be less than sigma yield. Yield is the, we measured from a simple tension test. Okay, so we plot them into a sigma 1, sigma 2 plane, these equations. Okay, sigma 3 equals 0 in two-dimensional case. Then this equation is simply, okay, simply we can draw like this and draw like that. Well, we have a, you can easily find out this graph from this, not that difficult. And compare with the Van Misses. Van Misses, we had this one, and Tresca have this one. And then those two theories are giving us a little different region, especially here and here. So in this region, Van Misses are saying that material will not fail, but according to a Tresca, this is dangerous and this will fail. So you can see that Tresca is a more conservative, more smaller, meaning that would not allow designer to design the stress is a little bit, smaller space, the smaller space. But just understand this concept. And then now, what if we have a sigma x is not the 0? Well, that is the one, I would say, this guy. This guy, multi-axial. So multi-axial means that sigma 1 and sigma 2 and sigma 3 principal stress. This is the three-dimensional space. So sigma 1 and 2 and 3. Two-dimensional, we can say sigma 1, sigma 2, shear stress is 0. Why shear stress is 0? Because it's a principal stress. And then three-dimensional like that. Now we are trying to, sigma 1 and sigma 2, you have a plot, sigma 1 minus sigma 2. You can see that Van Misses is like that and Tresca was like that. Now we can consider another axis, sigma 3, and then sigma 3, and then referring to that previous equation. So this is a sigma 1, 2, 3, and then this is the one we represented by, remember that the sigma 1 minus 2 square plus sigma 2 minus 3 square, sigma 3 minus sigma 1 square, and divide by half, and the root less than sigma yield. So we can plot them in three-dimensional space, and this is the one. And then sigma 3 equals 0. 3 equals 0. We had this graph, and this is this one. So what do we call this? Is the equivalent stress or sigma Van Misses stress. We can do the same for the Tresca. We can draw very much similar. This is a very important concept. And if we look at the this three-dimensional space, like the sigma 1 and 2 and 3, and then this surface will be like this. Like this is important. So when you design the structure so that all the stress, principal stress inside, you are safe. We are safe. But if the stress is above, outside of this criterion, what will happen? Material will fail, or material will have a permanent deformation after unloading, which is not what we want. So so remember, this is just a circle. If we look at from here, okay, we look at here, and then we can see this is a circle. So from this observation, very interestingly, this line is represented by this point, and then it doesn't matter how big, how large this line, but as long as you have inside this cylinder, we are good. We are safe. Okay, this is another understanding of the failure criteria. Okay. See, I'd like to go back to this one. What we learned is that only this guy, we had a strength, and now stress less than strength. This is a failure criterion. So when we design the stress, let's say this is a force, and then this material is Young's modulus, and then certain deformation, and the force is applied to a body like the cross section A, then stress will be the sigma, and the strength will be the yield and less than. But if this stress is a three-dimensional, all you need to do is that to get the this principal stress, you know, now we can say that equivalent stress, bond mass stress should be less than yield, or Tresca tau maximum, maximum shear stress should be less than sigma yield minus divided by 2. These are two different criterion. Actually, when we design, we often prefer to use these bond misses rather than this. This is a little bit simpler to obtain. So bond misses stress and this. Okay, so we are at here, and we understand how we design, and the I'd like to share with you what is bond misses stresses. And now here, you can easily try in Google and Chrome browser or any browser. Bond mass stress is the scalar. Scalar is the important. Scalar means that no longer a tensor. This is simply one value. Simply one value. Sigma equivalent is the one value. One value means that, you know, no longer see this one is the one value, just a scalar quantity, one value. That's what it means. A scalar value used to predict when a ductile material. I didn't say that, but ductile means that in 45, very weak to a shear stress, ductile material will permanently deform. See, we emphasize permanent deform or yield under complex loading. Complex loading means that a three-dimensional case. So how it works, decomposing stress and focus on the distortion, and so on and so on. And I'd like to say that how widely used this concept in every design of structures. Let's say you under bending, you can see the structure will deform and permanent. Well, this is the result of the computer-aided engineering, CAE, and this giving us all the complicated stress state. And this is a very important tool, by the way. But the important is this giving us all the stresses, and this giving us all the stresses. And then every point we get what? Van Mises stress. Van Mises stress. We calculate that one, and then now we designer, we would know, oh, this material will fail or not, or permanent deformation or not. How? Well, we already have a sigma yield strength. See, this guy giving us a stress strain curve, and this guy is the well, graph looks very giving us a sharp curve, but this is the yield strength, right? So exactly same procedure as we did. We consider this, we consider that, and then okay, this one is the beam. And as you can see, under the load, what will happen? The red is always a signal, the critical hotspot. And then you can see tension and compression, and this is a maximum. And this material will fail here. This kind of distribution will be studied in beam theory later in our course. But right now, as you can see here, see, other guys will do experiments by changing the sigma 1 and sigma 2, and this is a point they observe. And as you can see, how the Van Mises and Tresca will match with the experiment. So this saves us a lot of effort. All you need to do is just measure the yield strength, and then you design. Well, of course, you need to calculate the all these stresses, but the stress calculation of complicated stresses like this is the now we will learn how computer-aided CAE, okay, computer-aided engineering. So CAE or CAD, we know that computer-aided design, computer-aided engineering, and then what else? Computer-aided manufacturing. Those are three important tools and methodology is very unique in mechanical engineering. So you should know how to design. I mean, design doesn't mean you just the conceptual design, but this is the computer-aided design. It's just a visualization. You should know how to visualize them. And we should know how to calculate the stresses. We should know how to manufacture it. So this is a very important concept. We have to understand very well. CAD, you know, the SolidWorks, CATIA is really critical tools you guys should have. And then once you have it, you should know how to calculate the stresses, CAE. And then once you confirm, you should know how to manufacture. So the CAD means that you just visualize, okay? CAE means that you can calculate complicated stresses. Again, we learn about the stresses like that, right? We learn the stresses. We learn the complicated stresses in a body like that. How do you calculate this one? Well, in a complicated situation, is beyond our simple, force equilibrium. See, this force equilibrium is sometimes really complicated, But in one-dimensional equilibrium, what does it mean? It means very simple, as is shown here. When you apply load, there is always a reaction. This is the equilibrium. But what if we have this and that and this and this and that, and then it's very complicated. Well, sometimes we have this, sometimes a torsion. What will happen here? It's a little bit complicated, but it's still equilibrium, okay? But equilibrium, not just equilibrium, we have a stress and strain and everything in there. So to calculate this one, that's why we learned the beam theory and torsion theory. But in general, we can calculate this one using the CAE procedures. Okay, that's why I know you guys didn't learn much about the computer-aided engineering, but this is the tools you guys. But the more important, you understand the concept. Okay, CAD is always a visualize what you have, and the CAE you just calculate the stresses inside three-dimensional way or two-dimensional, giving us a principal stress and boundaries, and then we can see, this material fail or not. This is a hot spot we have to avoid. Next step is manufacturing. We have to manufacture. We have to manufacture using the CNC tools, and anyhow we manufacture. That's the purpose of design. That's the purpose of analysis. So the concept of this, wide range covering the pretty much really all about the mechanical engineering. See, each department engineer will have their own strengths and weakness, and then feature. And these three, CAD, CAE, CAM, is the core knowledge and skills of mechanical engineer. In other words, out there, industry will hire you as a mechanical engineer. What do they expect? They expect you to design, you to analyze, you to manufacture. So this is very unique to a mechanical engineer. Other departments cannot do that. Say civil engineering, well, they don't know how to do this. Electrical, or computer science, or civil, or chemical engineer, they don't know how to do that. You will see that. This is a strength of mechanical engineer. So you always need to pay attention. I highly recommend you to get to, learn about this one as a mechanical engineer. That's why even computer-aided and AI is so hot, the industry will always like to hire you. Why? Because a mechanical engineer can design or analyze and manufacture. But these days, even computer CAD can be partly done by the AI. CAE can be done by the AI. Manufacturing can be done by the robot with the AI. So we have to compete with the AI, but at the same time, we have to get along with the AI. So that's the message I like to emphasize. How just the AI. Well, I'm sure it gives us a lot of when CAD meets AI, essential 2025. This is a new concept and new trend which occur everywhere in the world, and not just in now, but from in the future as well. Essential guide to a CAD and CAM CAE. So AI is very exciting, but you guys have to learn and to compete with the AI, and then to get along with the AI. So I cannot emphasize enough, really, the importance of AI. But to do so, we have to know what's the concept of the CAD, and then CAE, and stresses, and material failure, and etc. So that's the purpose of our class, the strength of material. We purpose of a design. Okay, manufacturing a little bit later, but okay, to come to a CAE, usually you need to define the what geometry. You always need to, let's say you have a design very simple, a click link. Uh, Now this is a CAD. I'm sure you can draw this one using the SolidWorks or Fusion 360 or very simple. But you should know how much stress occur here, and then that's the uh, uh, very important. See, you know what it is, right? Two clicks, you connect, and you just push it and then get it out. Simple connectors. Now, over the time, you just keep doing that. You should know how much the stress here, because someday this may fail. There could be some uncertainty, so you should know exactly how much stress occurs. This is what we are learning in this solid mechanics. Uh, but this is a little bit complicated. Uh, that's why we need to use a CA tool. But fundamentally, you need to understand stresses. 3 plus 5 plus 1 concept is exactly the same here. So giving us all the stresses and giving us all the parameter stress, and then we now are able to design. Okay. Uh, okay. Let's have a break. 10 minutes. It is 2:28. Let's have a 10-minute break. Let's come back to 2:40. Thank you. 자, 어, 어, 바로 전 시간에 내가 좀 수업을 좀 빨리 진행을 했죠. 그래서 아마 처음 이거를 접한, 뭐, 당연히 처음 접했을 겁니다. 이, failure criteria, 파손 이론, 응력 변환, 뭐, 응력 변환을 지난 시간에도 그렇고 지금 계속적으로 지금 반복을 합니다. 내가 반복을 하는 이유는 여러분 잘 알 거예요. 이게 지금 티어리나 컨셉이 여러분들한테는 새로워요. 아주 새롭습니다. 마치 let's say we are back to elementary school. 그러면서 지금 벡터를 배웠다고 생각을 해보십시오. 뭐 온도, 뭐 질량 이런 건 아는데 벡터? what the hell is 벡터? 하고선 막 머리가 복잡할 거예요. 그랑 똑같습니다. 여러분들이 새롭게 이제 스트레스를 배워요. 그래서 지금 복잡하고 이해 안 되는 게 당연해요. 그렇지만 아주 중요한 거는, 어, 약간 그 흐름, 이걸 왜 배우는지, 이걸 어디다 쓰는지의 그 이해만 확실히 해주시면은, 어, 그게 중요합니다. 그러면서 다시 한번 반복을 하면서 또 반복을 하고 계속적으로 여러분들의, 브레인을 여기에 익숙해져야 됩니다. 그러기 위해서는 한 번 깊게 하는 것보다는 계속적으로, 어, 반복을 하는 게 매우 중요합니다. 네, 지금 소리 잘 들리죠? 오케이. 어, 그래서 나도 지금 계속 반복을 하는 거고, 지금 많은 메카니컬 엔지니어링 스튜던트가 지금 4대 역학, 뭐 정력학, 재료역학, 뭐 동력학, 연력학을 배우면서 재료역학 어려워 하고 뭐 어쩌고저쩌고 그러는데 그럴 수 있지만은, 그거는 딱 한 번만 보고, 그 다음에 많은 거를 습득하려고 하는 그런 욕심 때문에 그래요. 이것을 계속 반복적으로 생각하고, 또 중요한 거는, 이거를 왜 배우는지, 어, 여러분들은 한번 상상을 해보면, 여러분들이, one of the ideal company you like to work in is the 현대. 현대 자동차에 가서 여러분들이 뭘 할 것 같습니까? 현대 자동차를 만들 거예요. 이제는 이제 현대자동차가 자동차 회사가 아니라 it's no longer just automotive company, it's now a robotic company. 로봇을 제작을 해야 돼. 그 로봇을 어떻게 걸어가게 하느냐, 동력학을 해야 되고, 얘가 어떻게 막 힘을 받고 할 때 이 바디를 어떻게 만들 것이냐라는 그 응력을 계산하고 해석을 할 줄 알아야 돼요. 어, 여러분들이 진짜 이거는 지금 뭐 1, 2년 남으면 이제 진짜 여러분들이 이제 현장에 이제 가야 돼. 어, 지금 먼 스토리가 아닙니다. 여러분들 in high school, you learn about all the theory 뭐 하기 위해서? 시험 보기 위해서. 항상 you study. Why? The purpose of studying is just to prepare for examination. 근데 이제는 그런 게 아니에요. 여러분들이 실제로 여러분들 손에서 자동차가 만들어지고 여러분이 로봇 만들고 또 뭐 그 비행기도 만들고 해야 돼요. 우리 지금 카이라는 회사 아시죠? 카이가 얼마나 자, 나 보세요. 나 보세요. 또 스크린 스크린을 통해서 나를 보세요. 다른 거 보지 마시고 여러분들이 이제 비행기를 이제 설계를 해야 돼요. 거기 여러 가지 하중이 가해지는 거. You need to understand how much load will apply to an airplane, and then you need to be able to calculate how much stress. 그 다음에 어떻게 하실 거예요? 이놈의 날개가 부셔지는지 안 부셔지는지 판단을 해야 되지 않겠어요? 이놈의 날개에 얼마만한 복잡한 스트레스가 발생되는지를 알아야 되지 않겠어요? 이제 그거를 지금 우리가 배우는 겁니다. 자동차도 역시 마찬가지예요. 우리 현대자동차 is now number one in the world. 그게 지금 현실이에요. 밖에 나가면은요. 그러니까 미국이나 유럽 가면은 현대 is considered as a number one automotive company. 옛날에 막 이렇게 뭐 10등 바깥에서 이렇게 막 주저하던 그런 회사가 아니에요. 거기에 이제 여러분들이 가서 여러분들이 능력을 발휘해야 돼요. what would they expect you to do? 이제 여러분들의 창의성은 지식에서 나옵니다. 여러분들이 많이 알고 있고, 많은 그 베이스를 가지고, 거기에 여러분들만의 이제 창의성을 가지고 이제 설계를 하고 해야 됩니다. 그래서 지금, 아, 여러 번 얘기했지만은 이거를 왜 배우는지, 이걸 가지고 내가 복잡한 이케이션 내가 빨리빨리 했죠? 그거 사실 중요하지 않아요. 왜? 아니, 뭐, 교수님 렉처 노트 있고, 뭐, 인터넷에 다 있는데, 그거 못하라 다 그거 외워요. 중요한 건 이제 이케이션입니다. 자, 그러면서 이제 내가 여러 번, 가만있어 봐. 뭐, 체크가 왔는데, please check the mic. That was your problem. Okay. 지금 스크린이 쉐어가 됐나요? 네, 그래서 저는 여러분들이랑 같이 수업을 하면서 매우 익사이트합니다. 지금 예를 들어서 지금 챗GPT입니다. I'm sure most of you are using the ChatGPT, but I like you to remind a different way of using the ChatGPT. 이게 지금 뭐 여러 가지 이제 나 같은 경우 이제 프로젝트를 좀 많이 만듭니다. 이제 각각의 어, 그 이벤트라든가 뭐 여러 가지에서 여기 뭐 어, 어, 지금 네 자꾸 내 화면 보여요? 공유돼 있어요? 오케이. 어, 지금 뭐 내가 이렇게 퍼스널한 거라면 꼭 보일 필요는 없지만은 어, 예를 들어서 뭐 캐세이라고 지금 뭐 그 여러 이제 큰 회사가 하나 있는데 거기랑 여러 가지 뭐 비즈니스 플랜을 짤 때 여러 가지 라든가 일단 중요한 거는 내가 지난번에 여러분들이랑 하나 그 프로젝트를 만들었어요. 솔리드 미케닉스. 그래서 첫 번째 클래스에 우리가 이제 챗GPT가 우리랑 챗GPT is with us. Okay? We ask him to help us. 그래서 what point should I emphasize uh, in the first class of solid mechanics? 그래서 쭉 갖고 여러분들한테 쉐어했어요. 그래서 오늘 그 두 번째로 지금 한번 uh, what is the stress transformation? 얘가 뭐라고 대답하는지 알아봅시다. 물론 그 이유는 그거예요. 내가 하성규 교수가 계속 강조하는 거는 could be my personal view. 내가 여러 가지 이유 때문에 나의 전공 때문에 내가 스트레스 트랜스포메이션 이렇다라고 강조하는 것 같지만 할 수도 있겠죠. That can be my personal view, but let's take a look at let's hear what ChatGPT says about the stress transformations. You know, the ChatGPT is much super than I am, and then his knowledge, and all the experience is huge. Now, stress transformation. Okay, 이게 좀 글자 폰트가 좀 작은 게 좀 잘 보이나라 모르겠다. Stress transformation is a method in mechanics of materials, solid mechanics, used to determine a stress acting on a material when viewed from a different orientation. 이해되죠? 오케이, 이해되죠? different oriented coordinate 시스템에 대해서 뭔가 거기에 이제 액팅하고 있는 스트레스를 지금 보고 있는 거예요. Along the X and Y plane, 그러니까 different plane. Why it is important? Helps analyze stress on an inclined or arbitrary plane. That's exactly what we learn. incline or arbitrary plane이 뭐예요? 지금 X 프라임이겠죠. Y 프라임. Used to find the principal stress. 우리 principal stress 강조했죠. maximum and normal, minimum normal stress라는 거 강조했죠. used to find the maximum shear stress 배웠죠. essential for failure criterion. 제가 얘랑 뭐 상의한 것도 아니고 나의 오랜 35년간의 솔리드 미케닉스, 스트렝스 머티리얼에 익숙해서 여러분들이 강조하는 거야. 얘도 챗GPT도 지금 exactly 지금 강조하고 있어요. 얘가 나의 렉처노 들어본 거 아니에요. 얘가 온 세계의 오랜 기간의 자료들을 합죽해서 얘기하는 건데, as you can see, the exactly same point I emphasize and what you are learning. General 2D stress state, I don't want to repeat. This is exactly the stress transformation in terms of 2 theta. And special case, principal stress occur when shear stress is zero. And graphical method, more circle, and so on and so on. Now, his reaction is that, would you like me to also drive the equation step by step? 뭐 이런 거 필요 없어요. 필요 없습니다. Now, 그러니까 얘가 지금 뭐 multiple failure criteria, great question. 왜 그러겠어요? 이게 맞아. 당연히 지금 다음 넥스트 스텝이 이거예요. 어쩌고 저쩌고 뭐 이거 뭐 반미스 스트레스 이게 이렇게 된다는 거, 모스클 티어리 맥시멈 스트레인 이런 겁니다. 내가 이거를 똑같은 내용을 왜 반복하냐? 지금 내가 강조하는 게 나만의 퍼스널 뷰가 아니라 여러분들이 실제로 현장에서 어, 마주치는 거예요. 내가 한번 물어볼게 얘한테. 그래, okay. Let's say how do we use the procedures? Uh, okay, how do we follow the procedure, the design automotive, please in Korean. 이게 지금 여러 가지 과정을 지금 이 자동차 설계에 한번 설명해 달라고 했어요. 자동차 부품을 설계할 때 응력해서 파손 기준 안전계수 적용으로 이어지는 절차를 따릅니다. 안전계수는 뭐 나중에 배운다. 제일 먼저 자동차 설계 시에 어, 그 I would like to say 어, 한국말하고 English. I asked him to show Korean and English together so that we can get more clear way. And then the first one, the road condition, 하중 조건 정의입니다. 차량 주행 시 발생하는 정적, is a static. For example, the vehicle weight and passenger and cargo 이런 것들을 다 이제 이거는 뭐예요? 3 플러스 1에서 맨 왼쪽 위에 로드에 해당하는 거예요. 하중 조건. 그 다음에 해석을 통합니다. 이제 구조 해석. 이것이 뭐 이퀄리브리엄이 기억나죠? 오른쪽으로 갔습니다. 이제 스트레스 어널리시스, 스트럭처 어널리시스. For the complication we cannot solve our way. We use the 유한 요소. 이게 바로 아까 얘기한 CAE 툴입니다. CAE 툴. 구조 해석을 해서 파손 기준을 적용을 해요. 그럼 여러 가지 뭐 반미스 스트레스라든가 이런 것들. 그 다음에 안전계수. 그러니까 뭐 자동차가 가다가 그래도 파손되고 그러면 큰일 나죠. 그래서 약간의 어떤 안전계수를 주는데 뭐 2 정도 줍니다. 그래서 피로도 이제 계속적으로 쌓이고 시험 및 검정. 어, 자, 여기서 바로 얘기하는 게 force가 아까 뭐 여러 가지 we have to consider static and dynamic and then stress analysis가 바로 요 equilibrium입니다. CA2를 이용한다 그랬죠. 그런 다음에 이제 여러 가지 스트레스를 계산하고 should be less than strength 요 지금 얘기를 하고 있는 거예요. 자동차를 설계하면서. 그래서 자동차 설계는 하중을 정의해야 되고 음, 그래서 지금 화면 계속 쉬어되고 있죠. 그래서 하중을 정의해야 되고 요거 외부에서 들어오는 하중을 정의를 해야 되겠죠. and 구조 해석을 해야 되고 여러 가지 구조 해석은 사실은 in a wide sense we have to consider all the procedures, but the most important point of this 구조 해석 is the equilibrium. 그 다음에 파손 기준 is strength and this is failure criteria. 그 다음에 여기에는 안 나왔지, 뭐, 이거를 가지고 뭐 실험을 해야 되고, 뭐 인증을 해야 되고 하는 거는 너무나 당연입니다. 플로우 차트로 바이링구얼로 정리해 드릴까요? 오케이, 예, 뭐라고 나오나 보다. 물론 당연히 이제 뭐 force, 뭐 equilibrium 어쩌고 저쩌고 나오겠죠. 그러나 여기서 지금 내가 강조하고 싶은 거는 우리가 배워야 되는 거는 어, 아, 이렇게 질문이 많어. 강조하고 싶은 거는 바로 이 프로시저의 이해고, 바로 스트레스를 할 때 이 스트렝스랑 어떻게 되는지를 이해하는 게 매우 중요하다라는 것을 다시 한번 강조를 합니다. 그리고 이게 지금 그 여러 AI에서도 지금 강조하고 있다는 거를 얘기하고 싶고요. 얘가 지금 뭐를 보내는가 한번 봅시다. 뭐 무슨 플로우 차트가 나오는지. 다운로드, 다운로드. 음, 네, 이 컴퓨터를 안 써서 그러는데, 아유, 이게 지금 좀 이렇게 되게 그 이상하게 나왔는데, 어, okay. That's the weakness of the ChatGPT. We can try the Gemini. This is another one, Gemini. Let me ask exactly same questions as we asked in the ChatGPT. Uh, I don't mean to compare, but I just like to emphasize that how 이거는 좀 크게 되는. 지금 여기서도요. 그 stress transformation is a method used in engineering physics to determine the stress component. 자, 여기 acting on a plane that is rotate with a respect to the original coordinate system. 그래서 이게 지금 우리가 지금 얘기한 건 노멀 스트레스가 뭐냐, 시어 스트레스가 뭐냐, 프린시팔, 맥시멈 뭐 거의 똑같은 내용으로 지금 강조를 하고 있습니다. 이게 바로 그 지금 트랜스포메이션, 스트레스 트랜스포메이션이라는 거죠. 지금 똑같은 질문으로 왜 이 스트레스 트랜스포메이션을 지금 배워야 되느냐라고 하는 겁니다. 여러분들이 그 머릿속에 비주얼라이제이션 하는데 인클라인 플레인에서 여러 가지가 일어나고 있다는 것을 꼭 이해를 하십시오. The simple answer is that we learn stress transformation to find the true maximum stress inside the material, which is crucial for predicting when and how it will fail. 그러니까 재료가 파손이 될 때 어떠한 면에서 어떻게 작용되고 있는지를 알기 위해서 스트레스 트랜스포머를 배운다고 하는 것이 펀더멘탈 이유입니다. 그러니까 혹은 더 weakest point, 어디가 가장 약한지, 왜냐하면 거기서 파손이 일어났기 때문에. So we like to confirm the safe structures. 그래서 그 제미나이를 하든 뭐를 하든 지금 다 똑같은 얘기를 하고 똑같이 강조하고 있습니다. 또 잠깐만요. 챗GPT가 요새는 AI 스튜디오라 해서 그 크롬에서 AI 스튜디오를 지금 제공하고 여기에 제미나이가 이제 기본으로 하면서 다양한 환경을 지금 제공을 해줍니다. 여기서 스트림 보면은 잠깐만요. 내가 많이 하진 않았는데. Hello, how are you?
I'm doing well, thank you.
We are in the middle of class, and I want you to emphasize how important it is stress and stress transformations.
Can you please tell me what subject or topic you
Uh,
are
Stress transformations.
understand forces acting on the material change when you look at them from different angles. This is crucial for designing structures that can withstand various loads without failing. Does that make sense?
지금 여러분들한테 지금 이게 소리가 들리는지 모르겠네. As I said, we are in the middle. No, I'm not talking to you. Say we are in the middle of class. I just want to make sure that your voice can be heard to our class, our students.
Understood. Is there anything else about stress transformations you would like to
Tell me a little bit about the failure criterion.
Failure criteria are rules that engineers use to predict when a material would break or deform permanently under stress. They help them determine the maximum stress a material can withstand before failing, which is essential for ensuring the safety of structures and machines. Are there specific failure criteria you'd like to know more about?
Okay, well, thank you. Bye. 자, 여러분들한테 다시 한번 강조하고 싶은 거는, 우리가 지금, 크게는, 스트렝스 오브 머티리얼 혹은 솔리드 메카닉스를 왜 배우는지, 도대체 어느 영역에 우리가 있는지, 엔지니어로서, 혹은 메카니컬 엔지니어로서, 이 바텀 업의 컨셉이 매우 중요합니다. Just rather than just, the focusing on local subject, you guys need to understand a big picture of the subject of the solid mechanics. Well, I'm a mechanical engineer too. I graduated from same university as you did. 제가 7과학번 메카니컬 엔지니어로 들어와서 여러 가지 여러분들 배우는 거 다 배웠고, 그래서 I happen to choose solid mechanics as my major. 어, 많이 배우면 배울수록 재밌어서 매우 해피하고요. 그리고 이것이 그냥 학문으로 끝나는 게 아니라 정말로 여러분들이 이제 새로운 설계, 제품을 이해하고 개발하는 거. 그 보면 이제 force가 있고 머티리얼이 있다 그랬죠. 그 머티리얼이 이제는 뭐 그냥 스틸이 아니라 뭐 다양한 재료를 여러분들이 개발할 수 있고 제품에 응용될 수 있습니다. 그래서 다시 한번 이 재료역학, 솔리드 미케닉스가, 여러분들이 앞으로 엔지니어로서, 이해를 하고 여러분들의 능력을 발휘하는데, 큰 기여를 했으면 좋겠다라는 생각을, 바람이 있고요. 그러니까 그 중에서 코어가 이 스트레스, 트랜스포메이션, 페일리어 크라이테리아. 아마 이번 학기 중에서 가장 핵심적인 키 아이디어입니다. 어, 그래서 근데 지금 이렇게 강조하고 또 AI도 강조하고 똑같은 내용으로 강조가 돼도 아마 여러분들은 아직 익숙하지 않기 때문에 좀 시간이 걸릴 겁니다. 그 시간을 줄이기 위해서는 어떻게 해야 되겠어요? 여러분들이 스스로 반복을 해야 되는 거고 반복한다는 건 여러분들이 계속적으로 생각을 해줘야 돼요. 그래서 여러분들이 거기에 익숙해져야 됩니다. 뭐 지식을 많이 얻자는 게 아니라 여러분들이 이렇게 이 토픽에 대해서 편안하게 다가와야 여러분들이 이제 그 위에 창의성이라는 게 이제 여러분들은 you guys are smart enough to come to any idea. 그렇기 때문에 물론 수업 들으면서 학점도 중요하겠지만은 이왕 배우는 거 잘 배우도록 하고요. Well, I don't want to go to a next chapter, but I just like to uh, share all the subject which we just learned. Uh, 그 여러분들이 지금 챗GPT랑 이런 것들이 그 무엇을 이렇게 정보만 가지고 할 수 있냐라고 그런 거 당연히 아니겠죠. 그래서 가만 있어보자. 화면이 또 강조하고 싶은 게 바로 우리가 엔지니어로서의 프로그래밍 스킬입니다. 프로그래밍이라는 게 뭐 아주 그냥 뭐 복잡한 그런 것이 아니라 지난번에 우리가 엑셀 프로그램을 어, 좀 봤지 않습니까? 그 엑셀 프로그램이 하는 역할이 뭡니까? 우리의 모든 지식을 집어넣고 거기에 어떤 밸류가 들어갔을 때 즉각적으로 우리가 여러 가지 스트레스를 얻어낼 수 있는 그런 과정이죠. 그래서 그걸 다시 한번 오픈을 하게 되면은 어, 그리고 이 엑셀도 그냥 감 넣고 그냥 보시지 말고 그것의 의미를 이제 익혀가면서 이 스트레스들이 이렇게 업앤다운 하고 시어 스트레스가 어떻게 움직이고 여기에 주어지는 다양한 하중에 대해서 지금 이 컴포넌트들이 모서클도 중요하지만은 이 그래프로 일단은 뭐 같은 내용입니다. 근데 단지 이거를 막 돌아가면서 플롯을 그냥 하나의 서클로 한 게 모서클인 것뿐이고 모서클에서는 즉각적으로 뭐예요? 맥시멈 스트레스, 미니멈 스트레스, 시어 스트레스를 즉각적으로 알 수 있는 겁니다. 그거나 이 지금 그래프로 표현되는 거나 컨셉은 같다라고 이해를 당연히 해줘야 되는 거고요. 그 다음에 여기서 보면은 이게 이제 스트레스 스테이트라는 거는 이제 이해가 되겠죠? 2, 2. 만약에 내가 이거를 0이라고 치면 어떻게 되는 거겠지? 아, 이게 두 개가 프린시팔 스트레스에 해당하겠죠? 프린시팔 스트레스. 아, 그런데 이게 앵글에 따라서 스트레스가 아무리 각도, 아니, 그러니까 각도 인클라인이 돼도 안 바뀌어. 왜 그럴까요? 어, 그, 그러니까 E라는 스트레스 스테이트가, 모서클로는 어떻게 돼요? 아, 점이죠, 점. 네? 2, 0도 여기고, 또 Y점 투제로도 여기죠. 그러니까 X하고 Y가 같아요. 그러니까 그 얘기가 뭐 그거 같아요. 그냥 한 점이기 때문에 아 스트레스 트랜스포머이 항상 같다라는 의미예요. 그러니까 그래프로 표현하면은 여기서 만약에 이 똑같다 그러면은 옆으로 이렇게 해도 다 똑같다. 시어 스트레스가 전혀 안 나타난다. 이겁니다. 이러한 거라든가 뭐 예를 들어서 우리가 아까 배웠던 제로에 아까 여기 뭐 티어 스트레스를 가해주면은 어, 티어 스트레스에서 이게 시어 스트레스가 플란트한 게 이, let's delete this guy. 티어 스트레스인데 이게 시그마 X 프라임 X 프라임 빨간색이 쉬어 스트레스니까 없었죠. 그러다가 45도 되면은 피크를 치죠. 이게 아까 그 모서클이랑 같이 연동이 됐으면 좋겠습니다. 이것이 이제 예를 들어서 한 번 더 여러분 당연히 알지만은 우리가 어떤 각도, 이 각도에서 이거 이 각도에서 요거가 각각 시그마 x 프라임 y 프라임 x 프라임 y 프라임이 된다는 겁니다. 이게 앵글이 따라서. 예? 이게 이제 컨셉이에요. 그러니까 어떤 플레인이 내가 이게 자꾸 이렇게 잘라가면서 혹은 어떤 바디가 이렇게 있는데 내가 이렇게 잘랐을 때, 이렇게 잘랐을 때, 이렇게 잘랐을 때 여기서 나타나는 노멀 스트레스, 시어 스트레스가 다 달라진다라고 하는 내용이죠. 그래서 어떻게 바뀌느냐? 이 패턴이 항상 보면은 맥시멈이고 밑으로 갔다, 올라갔다, 밑으로 갔다. 그 얘기가 바로 보면은 원으로 표현된다는 거예요. 항상 올라갔다, 작아졌다, 올라갔다, 작아졌다. 시어 스트레스도 맥시멈 갔다, 미니멈 갔다. 이런 것들이 거고요. 이것이 이제 재료에 대해서 어떻게 파손되는가는 이제 어, 뭐라고 합니까? 우리가 이제 반미시스를 이제 배우는 거죠. 그래서 인베리언트 1과 인베리언트 2를 우리가 지금 했습니다. 좀 화면이 지저분. 자, 오케이. 인베리언트가 있었고 여기에 이제 아까 얘기하는 그 뭡니까? 스트레스 이퀴발런트 혹은 반미시스 스트레스를 한번 어, 찍어보도록 합시다. 반미스 스트레스 기억나요? 그러기 위해서 일단은 제일 먼저 프린시팔 스트레스를 먼저 하면 좋겠죠. 프린시팔 스트레스를 먼저 구해 봅시다. 프린시팔 스트레스, 프린시팔 스트레스가 어떻게 표현됐어요? 지금 이게 인베리언트 1이라는 게 지금 이 두 개의 점이라는 것이 바로 그 원의 중심이고 인베리언트가 바로 뭡니까? 그 반지름이라는 것을 이제 우리가 이해했죠. 그래서 인베리언2가 레디어스, 모터클에서 레디어스고 인베리언트 1은 지금 그 center of motor 입니다. 자, 그런데 여기서 뭐 2로, 그치, 2로 나눴구나. 오케이. 자, 그래서 여기 principal 1, principal 2 해서 principal 1은 어떻게 계산돼요? simply 잠깐만요. 우리가 이거 이름을 줬던가? 이름을 주지 않으면은 우리가 이거를 이름을 줘봅시다. 이거를 그냥 우리가 센터라고 부를게요. 그 다음에 이거를 레디어스라고 부를 거고요. 그 다음에 이만큼을 잡아서 이렇게 이만큼 잡혔나. 이거를 우리가 a define name, oops, 어, create from selection, top row 이렇게 지금 했습니다. 이렇게 해야 지금 principal 에서 이것이 센터 플러스 레디어스 하면 그냥 이케이션이 이 영역에 다 적용이 되죠. 그 다음에 그 프린시팔 2 미니멈은 뭐예요? 미니멈은 센터 마이너스 2가 되겠죠. 그래서 이게 프린시팔 스트레스예요. 그러니까 플러스 1 마이너스 1 이게 당연하지만 이거 왜 각도에 따라서 하나도 안 변해? 이거는요, 보세요. 프린시팔 스트레스라는 건 그 스트레스 주어진 데서 시어 스트레스가 0이 되는 포지션이기 때문에 각도에 따라서 안 바뀐다는 걸 다시 한번 당연하지만 느끼는 게 좋겠습니다. 그래서 프린시팔이 1과 마이너스 1이 되는 이유가 뭘까요? 아까 배웠죠. 시어 스트레스가 1이 있으면은 이게 어디서 일어나는 거는 얘기 안 하지만은 프린시팔 스트레스는 플러스 1이고 마이너스 1이다. 다시 한번 그림을 그리면은요. 시어 스트레스가 요거가 지금 이렇게 지금 가해지는 상태인데 프린시팔이 여기서 텐션이 가해지고 컴프레션이 가해지는 게 프린시팔 스트레스고 이게 모서클로는 쉬어 쉬어에서 이렇게 된다고 그랬죠. 그래서 여기가 센터고 여기가 지금 이게 R이 되겠죠. 뭐 이게 R이나 똑같은 얘기인데 프린시팔 1은 지금 이게 주어진 게 뭡니까? 1입니다. 이게 1이에요. 값이 1이면은 텐션 값이 지금 이것도 당연히 1이겠죠. 이건 당연히 마이너스 1이고. 그러니까 이게 1이 되고 마이너스 1이 된다. 그게 바로 1과 마이너스 1이 되고 그것은 calculate from a center 0 and radius is 1. And now stress equilibrium equivalent가 어떻게 계산이 될까요? Remember equal first square root 스퀘어 루트에 뭐였어요? 어, 그 프린시팔이란 거를 정의를 안 했네. sorry. 3차원을 고려를 하기 위해서 프린시팔 어, 3라는 거를 정의를 할게요. 이거는 당연히 뭐겠습니까? 0입니다. 우리가 지금 2디멘셔널 하기 때문에, 그래서 이거는 그냥 0이라고 그냥 값을 넣고요. 그나저나 요거를 네임을 먼저 정의합시다. 이렇게 정의해서 define name, sorry, create, create 탑으로 이렇게 해주면은 지금 아마 이게 스페이스는 저절로 그 프린시팔 언더바 1이라고 지금 들어가죠. 그래서 스트레스 이퀴발런트 이거 좀 조금만해서 다시 크게 할게요. 스트레스 이퀴발런트는 어떻게 계산되겠어요? 아까 equal SQ 루트에 그때 기억나세요? 프린시팔 스트레스 1 마이너스 프린시팔 2 가로 닫고 스퀘어에 플러스 가로 열고 다시 프린시팔 2 마이너스 프린시팔 스트레스 3 하고 플러스 가로 열고 프린시팔 3 외우기도 쉽죠. 이게 사이클리컬하게 외우면 이해하면 되니까 여기에서 가로 닫고 이렇게 스퀘어하고 가로 닫으면 되겠습니다. 그러면 2.444 어쩌고저쩌고가 반미세스로 오케이. 그리고 이게 지금 다 0으로 제시가 돼야 되고요. 그러니까 당연히 이거는 이제 바뀌지 않는다라는 거는 이제 다시 한번 당연한 얘기지만 강조하는 이유는 그러니까 이것들은 they don't change. 어, 그래서 이것이 그 불변량 그리고 재료가 파손이 될 때 이퀴발런트 스트레스가 각도에 따라 바뀌면 안 되겠죠. 어, 그거는 좀 더 스스로 많이 생각을 해봐야 되는데 반미스 스트레스가 이렇게 지금 나온다. 그리고 이게 좀 값이 이상하네. 여기 2분의 1이 빠졌네요. 2분의 1이 빠졌습니다. 스퀘어 루트 여기에 색채로 한다면 2분의 1이 있고 가로 열고 이것이 2분의 1로 이렇게 해야 될 것이죠. 그래서 2분의 1이 바깥에 그냥 있어야 되겠죠. 이렇게. 그래서 그 지금 시그마 이퀴발런트 스트레스가 1.2 이렇게 지금 나오고 있습니다. 이게 쉽게 얘기해서 만약에 우리가 1 항상 프로그램 할 때는 더블 체크 1 했을 때 0.777 이게 something wrong. This execution is not right. 0, 0, 서 제곱하고 이게 소리 이게 루트가 안으로 들어가야죠. 내가 다시 한번 그 이퀘이션을 보여드리면은 가끔 혼돈이 될 수 있는데 뭐 사실 혼돈할 것도 없습니다. 그것이 000을 대입했을 때 we can double check whether that is the correct or not. Let's say this guy. So this is 2, and equivalent stress will be given like that. Right? This one can be put here. This is the one. So, 스퀘어 루트 안에 들어갈 때는 바깥에 이렇게 된 거 맞죠? 자, 그래서, let's say 1, 0, 0, of course, we will have a radius is half and principal 1, 0, 0, and equivalent. Now, what will happen to, say, any value? Now you can see that the point of the concept of this stress equivalent is that one scalar variable which would represent this stress state. 그러니까 반미스 스트레스, 뭐 이퀴valent 스트레스라는 건 뭐냐면 우리가 이렇게 지금 복잡하게 스트레스 3개가 3개 혹은 4개가 혹은 프린시팔에 가서 9개가 있는데 그거를 대표하는 숫자 파손 관점에서는 얼마냐라고 얘기해주는 이론이다. 이만큼을. 그래서 우리가 시그마 일드, 시그마 일드, 시그마 일드라고 를 뭐 예를 들어서 뭐 일들을 축이라고 표현할게요. 이걸 이름을 이제 두게 되면은 시그마 일드보다 작냐 크냐를 이제 판단해 주면 되겠죠. 그러기 위해서 판단하기 위해서 가장 좋은 게 뭘까요? 이거를 시그마 일드로 나눠주면은 어떻게 되겠어요? 시그마 일드로 딱 나눠주게 되면은 짜잔 0.38. 그러니까 이게 10인데 그러니까 10에 비해서 그러니까 이거를 1이라고 봤을 때 0.38 이다. 그러니까 즉 예를 들어서 if we apply the stress is 10, 0, 0, what will happen? This will be 1. 1 means that okay, I would like to say the divide by the sigma yield. It will give us the simply how safe we are. And then let's say we like to say safety factor will be 네, 항상 이름을 먼저 줘야 되는데 자꾸 내가 까먹네. 이름이 너무 복잡하게 올랐을 것 같은데. That's okay. 그래서 safety factor is nothing but the 1 over this guy. 그 얘기는 자, 우리가 now sigma yield is 10. What if we apply the only 5? Of course, safety factor will be doubled. 안전계수가 2. 혹은 stress level is only 50% compared to yield strength. So this is just their relation is just a reverse. But depending on the how you interpret, how to understand, now is up to you. But industry wise, we are much prefer to use a safety factor. So this is a given. Okay, this is a given. Given. I always prefer to use the blue. And then now this guy is the design stress which you design. As a result of your design, we have a 3 components. Now this is easy to say, easy to understand the factor of 2. Now what if we have another component and another component? Now what if we apply the 12? Oops, safety less than 1, and then stress equivalent is the above the 1. That means we are not safe. Okay, we are not safe. So, for example, let's say 11 and 0. This is a very interesting situation. Is that the yield strength is 10. Now sigma xx is 11, which is bigger than yield strength. If we don't have a other stress, of course the safety factor will be less than 1, and it's not safe. But let's say if we have another stress component, if we have another stress component, how we can, well, you can see simply how they change that. Okay, how to change that. So the as an engineer, we need to understand the theory, understand the concept, and at the same time, we need to use these kind of tools, right? So everything is okay. Now let's get back to I didn't try yet, but let's try what it can do for us. 우리가 지금 let's say we are in the stress transformations here, and transformation explain. Now I like to develop a tool to calculate the van Missel's stresses. I mean, as I said, I like to develop a tool to calculate the van Missel's stress. Let's see what it says. I'm sure they not only displaying the equation, but they will also program for us. The reason it takes a little time is that I said it's a plant, a very important plant, which you have to supply. I like to develop a tool to calculate the van Mises stress. So starting point will be the certain stresses. I didn't say 2D or 3D. Let's see what it says. Awesome. I built you a small reusable van Mises stress calculation toolkit with a code and example. You can download everything here, Python modules. This is the, oops. Okay. So Python module and this, and what it does is the input is like this. And then Python module, you can easily copy this one. I need a manual of let's say I'm sure they calculate the program the code in Python, and now what we like to do is that we like to have a manual. This tool calculate. This is a manual, okay? The overview. This tool calculate the van Mises stress from a different stress state, plane and 3D tensor, principal stress, everything. And then a Python module and comment. This is the so you got the everything, even in CSV file. This is an Excel readable file, and then you can run if you have a Python. You can have a formula. This is a manual, and it can also explain and this manual MS Word and PowerPoint. Well, I don't want to go there, but now I like to input the stresses as in say 3 component in two-dimensional. Okay, so two-dimensional as in say sig x, sig y, and sig xy. Rather than just a metric, I say that we like to apply the 3 components like this. Now, say 1, 2, 2. 이런 폼으로 이렇게 1, 2, 2를 어사인 했습니다. 그러면 얘가 뭐를 계산하겠습니까? I'm sure it will calculate the Vamis's stresses. That's what he's doing right now because he already developed a Python code, and Python code Vamis's stresses in this 이걸 쫙 집어넣어서 3.87 and 이걸 했고 그 다음에 파이썬 코드의 그 결과치만 보이라고 하면은 당연히 이제 반미세스 스트레스를 보이겠죠. 여기서 1 to 2 하니까 3.87. So let's confirm with our Excel tools. Say 1 to 2. So 1, 2, 2. Then Burmese stress will be 3.8. Okay, sorry. 우리가 이 Burmese yield strength로 나눴구나. yield strength를 let's have a 1. So which will be the 3.873 exactly same. Principal stress and principal stress here. This is the first one, 3.56, and so on and so on. So the unit doesn't matter as long as they are consistent. Maximum shear stress is a 2.062, and maximum shear stress, which is the same as the radius, 2.06. 오케이. 그래서 지금 여러분들이 여기다가 뭐 10점, 15점, any value. 벌써 이 폼을 준다고 얘기를 했으니까, I'm sure this ChatGPT is smart enough to understand what I'm typing in. 10, 15, 3, it will give us the, okay. 지금 이렇게 빨리 이거를 봅시다. 10, 15, 3. 그래서 얘네들이 벌써 이거를 따따딱 하고 이제 준 것이 아까 뭐였습니까? 14점 반미세스 스트레스 줬죠? 프린시팔 스트레스 줬죠? 어쩌고저쩌고 지금 똑같은 거 뭐 당연하겠지만 why? Well, simply the theory is the same. So now let's define a yield strength as another input. Sig X, Sig Y, and Sig 아까 XY라 그랬나요? 그 다음에 시그마 yield strength 이렇게 주겠다고 하고, 예를 들어서 1, 2, 2 하고, 여기다 이렇게 해서, 다, will it fail? What is the, uh, safe factor를 한번 물어봅시다. So let's define yield strength as another input. So 저거 1, 2, 3 and 3. 이거 빨리 한번 해봅시다. yield strength가 3 and then 1, 2, 3. Then is a failure or what is the safety factor? Safety van Mises 얘가 he says 5 point van Mises 여기 아까 이제 디바이드해서 safety factor가 뭐예요? 0.54 and 0.54. This is exactly same as our research. Of course, we just like to double check and then we would not need this Excel file. We just ask ChatGPT to calculate anything. As you can see, 파이썬 코드를 여러분들이 얼마나 쓸지 모르겠는데 이거를 그냥 카피하고 하면은 that's it. As you can see that this guy is smart enough. I said input will be like this. So sigma xx like 이렇게 지금 벌써 지가 변수가 정해서 이렇게 하고 반미스 스트레스 우리가 지금 배운 거 그대로 했죠. 그 다음에 세이프티 팩터는 이렇게 했고 그 다음에 프린트해서 이게 출력으로 합류한 겁니다. 심플. 어, 어, 그래서 여기다가 뭐 앵글을 주고 뭐 플러스를 해라 뭐 이런 것들 뭐 쉽게 되겠죠. Can you plot the say uh, the variation of in stresses along with 180 미스타입해도 얘네들 뭐 다 이해를 하니까 오케이 make choose catch 그냥 프린시플 하지 말고 그냥 스트레스 variation of stress along with angle from 0 to 180 let's see what it shows 플랫 하라 그랬어요. 베리에이션 스트레스를 하라 그랬어요. 앵글을 따라서 from 0 to 180. That is exactly what we expect from this guy. 그렇죠? 우리는 뭐 이렇게 360도까지 했는데 180도라 그러면은 뭐 여기까지 이렇게 보이겠죠. 그래서 이 세 개의 스트레스 얘기 안 했어요. 그러나 he would understand 이 세 개의 스트레스를 이렇게 보일 거라고 예상을 합니다. 아까 이 스트레스를 이거를 준 게 맞나? 자, 어쨌든 그래서 이거를 플랫하라는 것보다 이것을 파이썬으로 플랫하는 것을 파이썬으로 만들어라라고 한 다음에 하면은 금방 이제 될 터인데 지금 what he's doing now is for himself develop the uh, 여기 PC 버전은 안 써봤는데, 이게 플랫을, 잠깐만, 여기 나왔다. 오케이. 이게 지금 시그마 X를, 이렇게 앵글을 찍은 건데, 이게 바로 우리가 얘기하는 이 빨간색 요 놈이죠. 아까, 맞나? 그렇죠. 시그마 X, 그다음에 시그마 Y 프라임, and then 시그마 E. 얘네 시그마 XY를 타우라고도 종종 씁니다. It's not the different, it's the same. 그래서 이거를 지금 이렇게 된 거예요. 뭐 어쩌고 저쩌고 다 했는데, 어, please plot them all in one graph. 우리처럼 이렇게 한꺼번에 다 플랫해서 한번 보도록 합시다. So that we can compare easily. 자, 좀 달라 보이는 듯 하지만 똑같아요. 보이죠? 이게 지금 이렇게, 이렇게. 지금 다, 이게 그 스케일이 약간 달라서, 달라 보이는 듯 하지만, 이걸 우리가 쭉 이렇게 앞으로 하면은, 똑같다는 거를 알 거예요. 뭐, 당연한 얘기지만은, I like to emphasize the how, important the concept. At the same time, you can, program easily. You don't need to program. You just say, uh, you want one ChatGPT program, you want result, you want plot, and do anything you can imagine. But most important point is that you should know what they are, what the stresses are, what the biases are. That's the prompt you can assign to a ChatGPT. You can get the exactly same result as a Gemini. So anyhow, well, as a last one, plot a plot the well, I just say plot the Moore circle, see what it shows. This is the Moore circle we just had, right? 자, 그래서 I'm sure you would know already what you can do, what the ChatGPT can do. I just want to emphasize again then how uh, all kinds of artificial intelligence AI can do for us. But again, the most fundamental point is that your understanding of the why do we need, what are you going to do with this stress transformation and understanding of the concept. Okay. Okay. See, Moore circle. See, says it says a sigma x, and so on. I think it's still drawing. Okay. Okay. Let's see, same. Well, should be same. Okay. So this is a Moore circle, and then you can plot and you can do anything you like to do. It gives us all the stresses. C plus R, they even use the same notation as we are using. C is the center and plus R. And probably ChatGPT is watching our class. But anyhow, this is the what I like to say, and then I like to have a copy this link and then share with you guys. Okay, I copy through the Katalog all our we have done in ChatGPT. And then I also copy this Excel, or give a little bit different versions. They are version 2. And then, as usual, I will make the YouTube class. Okie dokie. That's all I like to share with you today. And then hope that the point is that you guys need to keep thinking, okay? What the hell is the stress transformation and Mohr circle? What are you gonna do? If you are a mechanical engineer in Hyundai, imagine what can you do with this all the theory and steps? Okay. Thank you. And we need to schedule for next classes. But anyhow, I will share through Kato. Thank you. Bye.